To start with, my name is Jan Trnka. And I'll have today's lecture and probably a few lectures in the future. I met some of you in Dobronice, but not everybody, so hi. Can you all hear me and can you all understand? I have a bit of a cold, so it might be a bit trickier, especially at the back too. Can you hear me at the back? Yeah? Okay. Right. This week you started a new course in our subject. Do you know what it's called? What it's about? Okay, it's about metabolism, but it's called energy for cells. Today's lecture is going to be less about detailed metabolic pathways in our cells and how our cells produce ATP, etc., which is going to be what the rest of the course is going to be about. But today I want to talk about a much more abstract and much more general principles that doesn't just govern what happens in our cells, but that actually govern what happens in the whole universe. So we're going to be talking about universal laws that actually allow our cells and our bodies to actually do anything at all. So the topic of today's lecture, well, it's called what fuels our cells, but we're not going to be talking about fuels as such. We're going to be talking about the principles that actually make them move, that make them work. Traditionally, this topic in physics or in chemistry is called thermodynamics. Thermodynamics. Can anybody guess the origin of this word? What it's about? There are any Greek speakers? There might be. Yeah, it's got something to do with heat and. Sorry. Well, it has a lot to do with energy, but now we're talking just about the word itself. So yeah, correct. It's got something to do with heat, absolutely. And the dynamics. The movement of heat. Okay. Well, it's actually the power of heat, but anyway, the movement of heat. Correct. Okay. So this is the traditional subject. I'm not going to spend a lot of time talking about thermodynamics itself. Actually, that's about it. But I think it's important for you to actually have heard the word at least once, so that some of you after this lecture are super interested in thermodynamics. You can go and look in the literature, and that's where you'll find most of the principles explained and talked about in more detail. Right. As I said, the topic of the lecture, or the title of the lecture, is what fuels our cells. So give me some of your ideas or some of your concepts of what actually fuels our cells. And think out of the box. It can be very specific things, it could be very abstract things. What fuels our cells and our bodies?
Glucose.
Okay, glucose. Glucose. Lipids. Okay. Could we put all of these under nutrients? Okay, so that we don't have to list all of them. Okay, etc. Nutrients. Okay, nutrients.
Energy.
Energy. Heat. Okay. What was the other thing? Sunlight. Sunlight. Yeah. What else? You have to speak up. It's actually quite difficult to hear. And it's also helpful for me if you raise your hand at least a little bit when you speak, so that I can, pinpoint who it is. What was that? Sorry? Nothing? Okay. Anything else that may power or fuel our cells?
Hormones.
Hormones. Okay. Hormones.
Chemical reactions.
Chemical reactions, okay.
Air.
Air? Anything specific in the air? Oxygen, okay. Oxygen. Water, okay. We don't have a lot of time, but otherwise I would ask you, what do you mean by the fact that water powers? But yeah, okay. Oxidation. Enzymes. What else?
Surroundings in general.
Surroundings. Okay. Okay. Surroundings. That's a good way of putting it. Yeah. Any other ideas? Okay, my favorite so far is that our cells are fueled by love. That's my favorite. That's my favorite answer that I got. I think it was last year or the year before. I thought it was pretty good. Anyway, most of these things that we mentioned do indeed power or fuel our bodies and our cells in some sense. Some of them not so much, but most of them most of them are kind of trying to get to the answer. I'm going to start with one of these words, probably the most general one, and that's energy. Okay, so I'm going to start with that just to explain what energy is, what laws govern what happens to energy, and then later on in the lecture we'll get to the answer whether energy is the thing that powers cells indeed. All right, what is energy? Yep.
The potential to perform a work.
Excellent. Okay, so that's the textbook. That's the textbook definition. Okay, energy is a potential for doing work. Now, what is work? Yeah.
The change of position from one place to another.
Okay, so that's a definition of mechanical work. Okay, so we can take an object and move it somewhere else. Okay, and in that we perform work. More specifically, it's acting against a force. Okay. So that's mechanical work, but there are other kinds of work. What do they all have in common? They require energy. They do require work because it's work, so correct, yeah. I'll get to whether they require energy in a moment, but yeah. Say again? What about it?
Balance between both of them. So PD to KD, the conversion of storage of energy to the usage of energy.
Okay, so it's a conversion. Okay, so work is a conversion of potential energy to kinetic energy. Okay, is that always work? So I can see that you've heard of the subject a bit. So does it have to be work? Because there are other ways that are not work that can do exactly the same thing. Okay, to make it a bit easier to describe what work is, well, first of all, I think it's very important to say that work is a transfer of energy. Okay, so that's sort of answer to your suggestion that it requires energy. Well, it is the transfer of energy. Okay, so it's not that we need energy. Well, we do need energy in order to perform work, but it's actually the transfer. It's a type of transfer of energy. Okay, so work is a transfer of energy from one place to the other, or one type to the other. Okay, now in order to maybe get in an easier way to what work is, I'll tell you about the other way of transferring energy, and that's heat. Okay, so on one hand we have work, and on the other hand we have heat. Both of them are types of transfer of energy. Okay, it's just taking energy from one place and putting it elsewhere. And what's the difference between heat and work? Yeah.
Work is ordered, while heat is...
Excellent. Okay, that is indeed the difference. Work is an ordered way of transferring energy. Okay, so for example, taking the flask and moving it somewhere else, that's pretty ordered. Okay, if I hold the flask in my hands, I'm going to warm it up. But that's a very disordered way of transferring energy because the energy is transferred to the basically disordered movement of the molecules of water in the flask. Okay, we'll get a little bit more into what is work and what is heat later on in the lecture, but this is the basic distinction. Okay, does it make sense that work is ordered and heat is completely disordered way of transferring energy? Otherwise, they're exactly the same. They're transfer of the same energy. So heat is not a type of energy, the same way as work is not a type of energy. So you can't say there's so much heat well, you can say it, but thermodynamically you're going to be wrong. You can't say there's so much heat stored in water, okay? Because heat is a form of transfer of energy. It's not a form of energy. Okay, raise your hand if that made sense. Okay, okay. All right, so it's an important distinction, okay? There's no such thing as heat energy, okay? It's just a way of transferring it. Either we can transfer energy in an orderly way, in that case it's work, or in a disordered way, in that case it's heat, okay? That's all. All right, so we've defined very well what energy is. We've defined what work is and what heat is. Now we'll get to one of the fundamental laws of physics, one of the fundamental laws of thermodynamics. And that's the first law of thermodynamics, which says that energy is conserved. So it's the law of conservation of energy. A very, very important law. So I'm going to write it on the board. Okay, so first law of thermodynamics is the law of conservation of energy. Energy cannot be produced and cannot be destroyed, okay? I'll leave aside what some of you may know from relativistic physics that actually matter can be converted into energy. But let's leave that aside, okay? That just generalizes the law into conservation of matter and energy, okay? So let's leave that aside. First law of energy says energy cannot be made, cannot be destroyed. The sum of energy in the universe is constant. Okay? Raise your hand if you've heard of this law before. Excellent, okay? It's why I keep talking about it. It's really a fundamental law. And very often you'll hear people talking, or even textbooks, talking about that energy is produced in a chemical reaction. Okay, or that energy is consumed in a chemical reaction. No, it's not, okay? That would actually violate the first law of thermodynamics, which is one of the most fundamental laws, okay? So even though people say that, they don't hopefully mean it, okay? So it's very difficult, and I'll probably say it many, many times in future lectures as well, because it's so ingrained in the language that we just say it. But strictly speaking, that's incorrect, okay? Energy is not produced, it's not consumed. Okay, it's only transferred from one form to the other, or transferred from one place to the other. It's all that can happen to energy. Okay? Now, we can actually mathematically describe this law. It's a very simple formula, but I'm going to tell it to you because it's important. Right. So we have this value that's called internal energy. The symbol is U, for whatever reason, and it's called internal energy. Why internal? Because it's the energy that's internal to a system. Okay? So that's inside a system. What is a system? Yeah?
The thing and its surroundings, like
The where the process of
the object and its surrounding.
Okay, the object and its surrounding, or the system and the surrounding. Basically, a system is anything we choose to study. Okay? So if we're interested in the human body, we're going to say the human body is the system and everything else is the surroundings. If we're interested in a human cell, we're going to say this is our system and the rest of it, even the rest of the body, are the surroundings. If we choose a planet or a solar system, that's going to be our system and the rest is going to be surroundings. Okay? So a system is just a part of the universe that we chose to study. There's nothing else to it. Okay? So the internal energy of a system is basically the sum of all the potential and kinetic and all the other energies that are in the system. That's all it is. Okay? Now, probably a lot of you, or most of you, are familiar with this notation of delta. What does it mean, delta U? Okay, it's a difference or change in this case, internal energy. Right. Now, the first law can be formulated in such a way that the internal energy of a system can only change if we transfer some energy to it. Sounds trivial, but it's actually quite important. So the only way we can change the energy of the internal energy of a system is if we add some energy to it. Okay, it can't be created. Now, it will get slightly confusing with whether negative or positive numbers are going to be used. But anyway, as we said, there are two types of transfer of energy. One is Q, which stands for heat, And the other one is work, which is where the symbol is W. Okay? So the change of internal energy only happens when either heat or work or both are transferred to the system. Okay? Now, what I said about whether it's negative or positive, okay? So these symbols denote work or heat that is given to the system. If the system releases heat, or if it does some work, they're going to be negative. Does it make sense? Okay? So if we say, it's just a matter of definition, we can define it either way. And you'll actually find, I don't want to confuse you, but you'll find sometimes in textbooks when it says that delta U is equal to Q minus W. It's still absolutely valid, but in this case, the work is not the work that is done on the system, but it's the work that the system does on the surroundings.
Engineers use that.
Yeah, you'll find both notations. It doesn't matter, it's still the same formula, you just define the symbols in a different way. Okay, raise your hand if that makes sense, because if it doesn't, okay, that looks fine. All right. Okay, so it's just a slight confusion of whether the heat or the work is going to be positive or negative. Anyway, this is the mathematical expression of the first law. The internal energy of a system can only change if we either add or subtract energy from it. That's true for any system, presumably including the universe as a whole, which is what we said in the beginning is the first law of thermodynamics. Energy cannot be destroyed. Right. I think this is fairly simple stuff, but actually very important. One thing I'll say, this is an empirical law. Anybody say what empirical means, or what I mean by empirical? Yep.
Found by observation.
Exactly, okay? So this is a law that we discovered, okay, I'm not going to go into details, but we discovered by observing the world around us, okay? So it is indeed possible, or at least logically possible, that we'll find a part of space where it's not true. Okay? It's highly unlikely from everything that we know, but it's still possible. Okay? So it is an empirical law. It's something that is discovered in the nature. It's not a mathematical law where it's logically necessary that it has to be like that. Okay? Just so that we know what kind of law it is. Right. Now, continuing with the subject of energy, I'm gonna define another variable, another value that is slightly more complicated, but it's quite important for the rest of the lecture. And this variable is called enthalpy. Enthalpy. Okay, and the symbol is H. What is enthalpy? Enthalpy is basically a type of internal energy that's easier for us to measure, or rather the changes of which it's easier to measure. Okay, I'll explain that. Imagine that you're a chemist, you're performing in a beaker, you're performing a chemical reaction, and you want to find out how did the internal energy change in the beaker. Okay, you mix two things, something happens, and you want to know how much the internal energy of the system changed. Now, in order to do that, you would have to measure the heat that's being released or absorbed by the beaker, which is pretty simple. But also, you would have to measure the work that the system in the beaker does on the surroundings. What kind of work can a reaction in a beaker perform? Yeah?
Pressure.
Yeah, it has something to do with pressure, but...
Well, if it expands,
okay.
you would have...
Okay, so imagine that the whole system or the gas is produced in the reaction. For example, we mix sodium carbonate with hydrochloric acid, okay? Carbon dioxide is released. And the gas that expands against a pressure, the pressure of the atmosphere. And in order to be able to do that, it has to perform some work. Does it make sense? Now, this work is very difficult to measure, okay? You would have to have it in a isolate, you would have to measure pressures, and it's a very difficult thing to measure. So chemists came up with this very clever mathematical trick where they defined a new value, which is called enthalpy. Just define, I'm just going to write the definition, but it's not going to be very helpful to you, I think, but anyway. So they did this trick. They said, let's define enthalpy, which is equal to the internal energy plus pressure and the volume of the system. Pressure times the volume of the system. Okay, that's the definition of enthalpy. Why would they do it? Well, the thing is, for our situation in the beaker where we, performing a reaction, the change in enthalpy is equal just to the heat that's released or absorbed to the surroundings or from the surroundings. So we don't have to look at whatever work is happening, we don't have to measure it. The only thing that we measure is heat, and that gives us the change in enthalpy, okay? So delta H is equal to Q. Okay, just a mathematical trick, and the reason why I talk about it is that we're going to use enthalpy later on to define an even more interesting function, okay? One important thing, again, positive, negative numbers. As we said, we defined Q being positive if it goes into the system. The same thing is true with the change in enthalpy. So if the change in enthalpy is positive, it means that the system absorbs heat. Okay? If it's negative, it means that the system releases heat. You may have heard about exothermic and endothermic reactions. Raise your hand if you've heard of them. Okay? So this is just a different way of saying it. Okay? So for an endothermic reaction, enthalpy is going to be positive. And for an exothermic reaction, delta IH is going to be negative. Okay? And you can find enthalpies for various reactions in tables, and you can find them on the internet. So it's actually a very, very useful thing which we can easily measure, and we can use it in calculations, and we can find out whether a specific reaction is going to release heat or whether it's going to consume heat. Okay, so enthalpy, an important physical quantity. Right.
Excuse me?
Yes?
For which one was it positive and for which one?
Okay, for endothermic, it's positive. Okay, because the heat is being absorbed, it goes into the system. For exothermic, it's negative, it's being released. Okay, it's just a matter of definition, but this is how it's defined. Okay, right. So this is very briefly about the concept of energy. Okay, and the types of energy and some mathematical definitions that we're going to use later on. Now, we said that, well, we sort of implicitly assumed that what's interesting in the universe is not energy itself, because it's conserved, it's always the same. But what is interesting is whether it moves and how it moves and where it moves from and where it moves to. Okay? Those are the interesting things, transfers of energy. Now, the question that we should answer in pretty much the rest of the lecture is, what determines which way the energy is going to go? How is it going to transfer? Okay? And I'm going to give you an example, and we'll try to use the example to figure out whether, we'll see whether we can figure it out, what actually governs, what decides where energy is going to go. Can I erase this? Probably. Yeah. So imagine that we perform a very simple experiment. We have two blocks of aluminum, whatever you prefer. They're exactly the same. Okay? So let's say that they are 10 centimeters by 10 centimeters by 5 centimeters or whatever. Okay? Exactly the same, two blocks of aluminum sitting on top of each other. Okay? Now one of them, the top one, is at 25 degrees Celsius, and the bottom one is at 0 degrees Celsius. Okay, so the top one is quite a bit warmer than the bottom one. What will happen? Yeah.
Energy transfer from the upper one to the lower one.
Okay, and in what way is it going to transfer? Probably.
Conduction.
Yep. So, yeah, it's going to be through conduction mostly. But what type of? We said that there are two types of transfer of energy. It's going to be transferred as heat. Okay, so heat is going to flow from the top to the bottom. Okay, now my question is, everybody probably knows that, or is there anyone who disagrees? No. Okay, so everybody knows that from experience. This is what happens in the universe. The question is, why? Yep.
Maybe the universe to have a balance between things.
Okay, so it wants to be balanced. Okay, okay. Well, why would be my next question, but yeah, yeah.
The disorderly movement of atoms that interact with each other?
What about them?
Well, they would, in simplistic terms, bump into each other, transferring the energy into the colder cube.
Okay, why would it be more probable for the faster moving ones to bump and transfer energy into the slower moving ones and not the other way around?
Well, that's just a law of probability. If you have a lot of moving objects in one cube and very few in the others, they wouldn't transfer that way. Because the low ones would be moving.
Really?
In a very slow sense, it's not a zero.
Well, the number of molecules or atoms or whatever in those two blocks is the same. Just, you correctly said that the top one are going to be moving faster on average, and the bottom ones are going to be moving slower. Okay? But there's from what you said, you know, if you have a slower moving one and faster moving one, why should the faster moving one transfer energy to the slower moving one rather than the other way around?
So it collides.
Sure, it collides, and so what?
Then the energy is transferred. Then the energy is transferred.
Well, it's not that simple. Yeah? There was a suggestion or question at the back. No? No? Okay. Yeah?
Nature likes equilibrium.
Yeah, okay. So we had that it wants to equalize the two. Yeah? Yeah. Yeah, okay. So we talked about the faster ones having more energy, so it will transfer to the slower ones, but we still not quite, at least I'm not quite sure why it should. Yeah?
I don't know. The heat usually goes out, and so the heat needs to go out of the one. And
Right.
since it's in contact with the other one, it's going to transfer.
Right.
to the other.
Why doesn't the heat go from this one to this one?
Because the other one is not hot.
Okay, so yeah. Okay, so I think what most people feel, and that's why everybody guessed right what will happen, is that heat always flows, and energy always flows from the warmer subject, from the warm object to the colder one. Again, the question is why?
Second law.
Okay, we'll get to the second law, indeed. Do you have? Okay, second law. Okay, that's where we're trying to get. Yeah.
But it's not always going from the warm. If you have like the ice, it will be melting, so it will be the other way.
No, well, if ice is melting, then heat is transferred from the water around it or from the air around it to the colder one. So it's actually really true that that heat flows from the warm object to the colder. The question is why. Now, I'll just, because nobody mentioned that, but sometimes I hear it in lectures. People will say, well, energy will flow from the top one to the bottom one because there is more energy in the top one. Is there more energy in the top one? Really? Yes, there is. Okay, there is indeed more energy in the top one. Okay, it's warmer. We can imagine that there's more kinetic energy in the atoms. Otherwise, they're exactly the same. There's higher temperatures, so there's more internal energy in the top one than in the bottom one. Okay, so it is true that this has more energy than this one. Okay, but what I want to show is that that's not the reason why energy flows from the one with more energy to the one with less energy. And I'll show it very quickly. I mean, it's clear that nobody thought that, or at least nobody said that. But I still want to show it because that's what sometimes people think that is what decides, okay? Flowing from more energy to less energy. Now, imagine the same situation, but the top block is still 10 centimeters by 10 centimeters by 5 centimeters. But the bottom block is 1 kilometer by 1 kilometer. A massive, huge block of aluminum. Okay? It's still at 0 degrees. The top one is still at 25 degrees. Okay? What's going to happen? The same thing. Okay? Heat is going to flow from the warmer one to the colder one. But in this case, which is the one that has more energy? Okay, who thinks it's the top one that has more energy? Okay? Half the people. Who think it's the bottom one that has more energy? Okay, not that many people. Okay, I obviously didn't do the exact calculation, but that's why I picked a block that's 1 kilometer by 1 kilometer, an absolutely massive one. It's very, very, very likely, I think it's almost certain, that the bottom one has more energy. okay? Because the internal energy is the sum of all the energies of all the particles. So even though the particles here are moving faster, there are so many more particles in the bottom one that the sum is going to be higher in the bottom one than in the top one. Does it make sense? Okay? So in this other case, the bottom one has way more internal energy than the top one. But the heat will still flow that way. Yeah?
So the amount of particles determines the amount of energy.
In some way, yeah. So the energy of an individual particle times the number of particles is going to be the sum of all the energies in the system. So yes, in part it determines the total energy. Yeah.
But how can the enthalpy increase if the upper one has less energy?
Okay, we're still not quite there at entropy. Okay, so we're going to talk about entropy in a second. Okay. All right. So this is just to show that it's not about differences of energy. Okay? We have lots of differences of energy where energy will flow from the one with less energy to the one with more energy. Okay? It's not about energy, but as many of you already said or implied, it is about a different physical quantity that's called entropy. Entropy. Now, I'll go slightly back to the history of entropy, how it was discovered, and we're going to talk about what it actually is. In the 19th century, well, 18th century, 19th century, there was a huge development. Basically, the first machine that managed to transform chemical energy into mechanical energy was discovered, which was the steam engine. Okay? The steam engine was basically in the history the first machine that could use chemical energy converted into mechanical energy. And towards the end of the 18th century and beginning of the 19th century, there were lots of engineers mostly, not so much physicists, that were interested in how to make a steam engine as efficient as possible. Okay? What is the trick to make it as efficient? What is efficiency in this case? What is the efficiency? Okay, so it's basically the ratio between the work that we produce from the engine divided by the energy that we put in whatever form. Okay, that's the efficiency. And obviously, we're trying to get efficiency as close to 1. Ideally, we'd want to produce as much work as we put in other forms of energy. Okay. Yeah? So they were studying, they were trying to figure it out. There were lots of ideas what to do. For example, use a high pressure of steam, or instead of steam, use air. Okay? There were lots of suggestions. Now, a French engineer called Sadi Carnot was the first one to actually do a mathematical analysis of an abstract machine. I'm going to show you what his machine looked like, and found an interesting thing. The idealized version of a steam engine, and actually it can be generalized to any kind of heat engine. So any kind of engine that uses heat to produce work can be idealized in this way. It basically consists of a warm reservoir. Okay, so that's a reservoir of heat. Okay, at temperature T1. Now heat flows, heat Q1 flows to the actual engine. Does everyone know what steam engine actually looks like? What parts does it have? Raise your hand if you know that, or whether I should maybe explain it. Okay, very few people. Okay, very few people know it. So the simplest way you can imagine a steam engine is that you have a cylinder with a piston. Okay, you heat it up. Okay, probably not with a candle, but anyway, yeah. You heat it up. Whatever is here, usually it's steam, but doesn't have to be, expands as it's heated. So obviously the piston moves out. Okay, then. So this is the work that's performed. Then the piston comes back, you heat it up again, goes back, etc., etc. Okay, so this is the easiest way to imagine a steam engine. Okay, this is the principle of it. So anyway, Carnot analyzed it and saw that there is a warm reservoir. In this case, that would be the flame. Okay, it's the flame that's the warm reservoir. Then we have the engine, which is a cylinder with the piston, and heat is transferred to the engine, and work is performed. Okay. First very important thing that Carnot noticed, again empirically, was, well, sort of empirically, was that this is not sufficient. Okay? This would not work cyclically. Now, what do I mean by cyclically? It means that the machine would not return to the initial state. Okay? So it would do some work, but then it would end up being modified with high pressure or high temperature or something. You wouldn't get back to the origin. And that's not a machine that you want to use. That's not an engine that you want to use. You want to use one that always at the end of the cycle returns back so that you can reuse it and use it again and again and again and can actually, you know, do something. There was a question?
No, I was just going to say.
Okay. So for a cyclically working heat engine, for example, steam engine, you also have to transfer some heat to a colder reservoir. Okay? So T1 is higher than T2. Okay? So this is the principle of Carnot's analysis. This is what he did. And based on this, does it make sense that then there is a colder reservoir? So for this type of machine, the colder reservoir could be the atmosphere. Okay? So the excess heat is released into the atmosphere. So you don't actually have to have necessarily an explicit cold reservoir, though very often you do. You have a cooler there. And I'll probably explain why you have a cooler there. But in theory, you don't have to have it. It can be the atmosphere. But there has to be some place to dump some heat. Right. The first thing that Carnot noticed was that the efficiency, the maximum theoretical efficiency of a heat engine depends only on one thing. And that's the ratio of the two temperatures. Okay? So there was a huge discovery. Well, nobody noticed actually because he self-published the paper and everybody noticed only about 30 years later. But anyway, but it was a major discovery because that meant that there's very little point in trying to figure out a completely different principle of, you know, a completely different type of heat engine, because he knew that the only thing that matters in a theoretical heat engine, but actually for practical purposes as well, is the ratio of the two temperatures. Okay? And we'll probably get to some, well, actually, well, I'll mention it later on, okay? Because there's an interesting corollary for that. So anyway, this was Carnot's analysis. About 30 years later, a German physicist called Rudolf Clausius, you obviously don't have to remember the names, but well, he was Prussian, actually, but anyway. Rudolf Clausius looked at Carnot's work and tried to reanalyze it, because at that point there were new discoveries in thermodynamics. For example, the first law, which is quite important, that Carnot didn't know about the first law, okay? And he didn't know, because that's a bit of a historical aside, but obviously the conservation of energy was something that people felt a long time ago. They felt that energy is somehow conserved, okay? But they didn't know, for example, that work and heat are the same thing, okay? There's the same energy, it's just different kinds of transfer, okay? So Sadi Carnot actually thought that heat, well, he called it, and it was called then caloric, is actually a fluid. It's a type of invisible fluid that flows through the machine. And it's very interesting because his very astute and very useful analysis of heat engine actually was dependent on a model of heat that we know is incorrect. Okay, he thought that heat was an actual fluid. Okay, and he got the right answer, but based on a completely wrong model that we now know. Okay, so Clausius was, you know, better equipped for the analysis because he already knew that work and heat are the same thing. Okay, they're just different forms of transfer of energy. It's all energy. Now, Clausius looked again at the analysis and he noticed another very interesting thing. And that is that if we sum the heat transferred here divided by the temperature here, and the heat transferred here and divided by the temperature here, overall for the cycle, it's going to be 0. Well, for a theoretical engine, that's going to be 0. Okay, for those of you who've done some calculus, usually you find it in a differential form, so there will be an integral of dq over t, but it doesn't matter. It's basically the same thing. Okay. So this is what he noticed for an ideal machine. Now, I'll give you a break in a minute. Okay, but what do I mean by ideal machine? The term in thermodynamics is called reversible. Reversible. Now, in normal life, reversible means that I can do something and then reverse it. I can put the chair up on the table and then I can take it down. It's a reversible process. In thermodynamics, it has a much more specific meaning. The meaning in thermodynamics basically says that a reversible process occurs by infinitely small steps. Okay? So, for example, you can imagine again, a cylinder with a piston, and now there's a pressure P1, and it's the same as the pressure in the surroundings. Okay? What will happen? Nothing. Okay? They are in mechanical equilibrium. Okay? Nothing happens. Okay? Now, imagine that P1, sorry, it should be probably P2, right? Now, imagine that P2 decreases by an infinitely small amount. Okay? It becomes smaller by 0.00001 Pascal or something like that. Okay? By an infinitely small amount. What happens?
will move outside by 0.
Okay, the piston will move out by an infinitely short, okay, amount of space. Okay, we'll just move very tiny, in a tiny little bit back. Now, if we, and the two pressures are going to be the same. Okay, so P1 again will be equal to P2. Okay, I know this is probably a bit too quick if you've not had a lot of physics, but okay, it's quite important. So we had the piston move out by an infinitely small amount. Now, we change P2, okay, back to the original value. We move it, we increase it by an infinitely small amount. What happens? Okay, it will again go back. This is the definition of a reversible process. It's a process that by changing the conditions by an infinitely small amount, infinitesimally, will reverse, okay? A normal process, like for example, heating the water in the flask, is not reversible because it's not actually happening by infinitely small steps, okay? My hands are much warmer than the water in the flask, so this is not a reversible process. I'm not going to go into huge detail, but the important thing is, first of all, that theoretically, the most efficient heat machine is a reversible one. So any real heat machine, which is not a reversible one, will always have a lower efficiency. Okay? So reversible is kind of the ideal. It's a theoretical ideal. Everything works better in a reversible process, and we'll get in a minute why it's important for our discussion. So anyway, this was Clausew's analysis for a reversible machine. So for a reversible machine, the sum of the heats divided by the temperature at which they were transferred is always 0. But then he noticed for an irreversible machine, it has to be less than 0. And again, it looks abstract and you think, why are we looking at it? And the next step is important. He noticed that this quantity, delta Q over T, or Q over T, has a very special property, and he called it entropy. So this is the definition of entropy. Okay? In a reversibly working machine, the entropy has to remain the same. Okay? I can see that you not probably. Are you still capable of getting the last bit of mathematics? Yeah? Okay. So this is the entropy of the actual engine. Okay? Sorry. Of the actual engine. It has to, or rather, it's the entropy that's transferred to the machine, to the engine. For a reversible engine, the entropy that's transferred to the machine has to be exactly the same as the one that's transferred to the surroundings. For an irreversible machine, the entropy that's transferred to the surroundings has to be bigger than the one that we gave to the machine. That's why it's less than 0. Does it make sense? Raise your hand if it makes sense. Not sure. Okay, so I'll explain again, okay? This quantity, which Clausius he looked at the analysis and he said, oh, this is interesting. Why should it be 0? Okay, this is interesting. So he said, okay, let's define that Q over T is a new quantity called entropy. He just defined a new quantity called entropy. He said, this looks like an interesting property for whatever reasons, okay? Now, what he noticed was that the entropy during a cyclical process, the entropy that's transferred to the engine in this process, okay? So some entropy, some S is transferred here because it's Q over T, and some entropy is taken away from it at this point. Does it make sense? Okay. Now he said he noticed in a reversible machine, this sum is going to be 0 overall. Okay. So whatever entropy the machine received, it also has to give out. Much more important for our normal lives is that for a irreversible machine, so for the normal machine that we actually get into contact with, not the mathematically ideal one, the sum of those entropies that are given to the engine has to be less than 0, which means that the machine in this process has to produce more entropy than we give it. Okay? Does this make sense? Right. And this takes us to the second law of thermodynamics. From this analysis of a steam engine, basically, which was based on trying to figure out how to make the best steam engine, Clausius and some other people, Lord Kelvin and others, got to the second law of thermodynamics, which is another fundamental law of the universe. And that says, there are again various formulations, but basically what I want you to remember is that the entropy of an isolated system, so of a system that does not communicate with anywhere else, always increases, or rather that it cannot decrease. Okay, it doesn't have to increase if you have reversible processes, but as we know, reversible processes don't really happen in nature, but let's say that for a reversible process, it's going to stay the same. For all other processes, it's going to increase. That's the second law of thermodynamics. For an isolated system, which we may assume that the universe is an isolated system, we don't know, but assuming that the universe is an isolated system, the entropy of the universe cannot go down. Okay? It can either stay the same, unlikely, or it has to increase. Well, I wouldn't get the expansion into that, okay? But so this is the second law. Can you raise your hand if you understand the second law? Super, super important, and we'll talk about it a little bit more in the second half of the lecture. Yeah, question?
I was taught that entropy is the tendency for disorder.
Yeah.
So, for example, is that a stable entropy is a cyclic, an ordered process, and when you increase the entropy, you're increasing the disorder. That's what I got because.
The definition of entropy as a disorder comes actually from Ludwig Boltzmann, which is he used a completely different concept in defining entropy. So this definition of entropy is based on transfer of heat. Boltzmann's definition of entropy and his mathematical work on it is based on statistical mechanics. So he looked at the individual particles and he thought, okay, what's going on? And from that he got a completely different concept of entropy, which is disorder. Okay. Now, in this case, the disorder is not in the machine because the machine actually has to return to the original state. Okay. So the entropy of the machine itself has to be the same in the end of the cycle as in the beginning, because that's what we said that we wanted to work cyclically. If we were just increasing entropy all the time, it wouldn't work forever. Okay. We want it to work forever. Again, that's mathematical idealization, but this is what it's about, okay? So the entropy of the machine itself has to be the same at the end of the cycle. The entropy of the surroundings is what increases, okay? So the engine actually gives off more entropy to the surroundings than it received from the surroundings. Okay? Let's have a very super brief 3 to 4 minute break, okay? Okay, during the break, a few people came to me and I noticed that there were a few misunderstandings or misconceptions about what I said. I can't really explain again a lot of it. But those of you who still feel you're not quite sure about what goes where and what is what, after the lecture we can go through it again. I just can't do it now because we have still some other stuff to talk about. But there was one thing that I thought was quite important. I can't remember, well, I can't see. But anyway, and that's the difference between heat and temperature, okay? So heat is energy that is transferred in a disordered way. Temperature is basically just a measure of the kinetic energies of a system. Okay? Those two are connected because we saw that if we have a difference in temperatures, heat will flow from the hotter one to the colder one. Okay? But temperature and heat are not the same thing. Okay? And also, I'm not sure I even said that, but T stands for temperature, okay? So T1 is a temperature, and in this case, it's thermodynamic temperature, so it's not in degrees Celsius, but it's in Kelvin, okay? Kelvin, can you raise your hand if you know what thermodynamic temperature is? Okay, so it's in Kelvin, fairly important, where there's absolute zero. Do you have any other questions that could be answered maybe briefly? Anything else to the first part? No, okay. So in the first part of the lecture, we defined what entropy is and how it was first discovered and how it was conceptualized. We already heard a few people said that entropy is considered to be a measure of disorder. Okay, this is not the classical definition. As you can see, the classical definition is Q over T. That's the classical definition of entropy. Ludwig Boltzmann then came with a different concept where he said it's a measure of disorder. It's not really a measure of disorder, it's rather the measure of how energy in a system is distributed, okay? If it's distributed as widely as possible, the entropy is high. If energy is only concentrated in one part of the system, the entropy is low, okay? Is low, okay? It's just something to help you think about what entropy is actually about, okay? But I think the classical definition is actually very helpful because a few people asked me, well, what is this entropy? How can it be transferred? It's not a real thing, okay? Well, the classical concept of entropy is helpful in that way that most common way of transferring entropy is by transferring heat. If you heat something up, in general, the entropy increases. Okay, again, that comes from the definition. Okay, so if you find it difficult, you're like, well, how can entropy be transferred? Well, usually it's by heating it up, and that increases the disorder, that increases the dispersion of energy in the system, etc. Okay, so this is what entropy sort of is. Okay, is it easier now to imagine what entropy? Okay, now the point where I talk about, or rather, we started talking about the question, what determines where energy flows and how it flows? The answer to that is the second law of thermodynamics. So the energy will only flow in such a direction from a system to a system or from a form to another form, so that the entropy of the whole isolated system, or the whole universe in this case, increases. Okay? And that's the direction where it's going to flow. Now, obviously, and there was another question during the break, we can have a small part of the universe or of the system where locally entropy decreases. But overall, entropy has to increase. So, for example, our cells, when they synthesize a protein or when they synthesize a nucleic acid, the entropy of the molecule itself is going down, okay? If you have individual nucleotides or individual amino acids and then you join them in a highly ordered structure, the entropy of that bit is going down. But the surroundings, the entropy of the surroundings has to increase by a larger value than by which you decrease the entropy of the molecule. Does that make sense? Okay? So everything that happens in the universe is basically directed by the fact that overall we have to keep increasing the entropy of the universe. Okay? A very fundamental, very important law of thermodynamics and of physics as a whole. Now, we as biochemists or doctors or whatever, it's not an easy, it looks like it's not an easy thing to do to measure the entropy of the universe, okay? Because if we want to know what happens, if the reaction is going to go that way or that way, basically what we have to do based on the second law of thermodynamics is to measure the entropy of the universe, because that's the only thing that tells us, or the change in the entropy of the universe, that's the only thing that tells us whether the reaction is going to go that way or that way. Okay? We're talking about the reaction. Let's look at an imaginary chemical reaction of A with B. And it's being transformed into C plus D. And in this case, we say that the reaction is reversible. Now, this reversibility is not the thermodynamic reversibility, okay? This reversibility is just the ordinary sense, okay? So A plus B reacts to give C plus D, but C plus D can also react, go back and react with A plus B, okay? It's a reversible reaction. Basically, all the reactions that you will ever see are reversible, okay? Even though some of them, you know, it's quite difficult to reverse them, but most of them are, almost everything is reversible. But that's an aside, okay? So we have this reaction, and we want to know which way is it going to happen, which way is it going to proceed. Is it going to proceed from A to B to C plus D, or the other way around? As I said, based on the second law of thermodynamics, in order to do that, we would have to imagine the universe with this reaction going this way, see how much entropy there is. Then we would have to see the universe with the reaction going the opposite way, and we would compare the two universes, and in one of them, the entropy is going to increase, in the other one, it's going to decrease, and we'll say, okay, obviously it's going to proceed in the way that entropy increases, okay? That seems like an impossibility. But again, thermodynamicists and chemists and physicists are so clever that they actually found a way to measure that, to measure exactly that. And that way to measure it is another quantity which is called Gibbs energy. Gibbs energy. Gibbs energy is defined as enthalpy minus temperature times entropy. That's just the definition. It's not going to actually tell you anything. Well, unless you're a thermodynamicist, okay? That's the definition, okay? Enthalpy we saw before. So that's a form of internal energy plus this P times V. We saw thermodynamic temperature, T, and we saw entropy as well as S, okay? So that's the definition of it. If we take the change in Gibbs energy, then we can transform this equation into delta G. The change in Gibbs energy is equal change in enthalpy minus temperature times the change in entropy. Do you understand just the maths? I'll explain why it's helpful in any way. Do you understand? Raise your hand if you understand. Yeah? Okay, good. Now, in order to be able to understand why change in Gibbs energy is so useful for us chemists to actually see what happens to the universe, the first important thing is, what is this entropy? Is it entropy of what? This entropy here in the definition is the entropy of the system that we're interested in. So I'm going to put system, for example, of our test tube, our beaker, our cell, our body. Okay? So this is the entropy of the system. Now, in order to measure the entropy or the change in entropy of the universe, we have to know the entropy in the system, and we have to know the entropy or the change in entropy in the surroundings, right? If we have the system and we have the surroundings, we have the whole universe. Yeah? Okay, now, where in this equation is the entropy of the surroundings? Indeed, delta H, because you'll remember that under certain conditions, and those are the conditions that we're usually interested in, delta H is equal to, we had it, yeah? Very good. Is equal to Q. And we know from this equation, from Clausius' definition of entropy, we know that Q is equal to Ts. But in this case, the S is not the entropy of the system, but it's the entropy of the surroundings. Okay? So putting the two together, the delta H and the T delta S of the system, we actually measure the change in entropy of the whole universe. Okay? Now, I'm not going to go into how this whole thing is derived, but I'll just say one thing, that delta G has basically is the negative value of the entropy. So if delta G is negative, the entropy is going to be positive. Okay? Let's now, do you have any questions to that? Okay. Let's look at it graphically. Let's have a graph for this reaction, for this hypothetical reaction. On the y-axis, we have Gibbs energy. Okay? On the x-axis, we have what is called the extent of reaction. So we start with pure A plus B, and we end with pure C plus D. Okay? It's the extent of reaction. Raise your hand if that makes sense. Okay. Now, what is the change in Gibbs energy going to look like for this reaction? Well, it's going to look something like this. So we start with a pure reactants. We're going to start at some pretty high level of Gibbs energy. With a pure products, we're going to probably get to some pretty high level as well. And in the middle, we're going to have the minimum of Gibbs energy. Okay? Now, I said that Gibbs energy, or the change in Gibbs energy, tells us how much the entropy of the universe is going to change, or has changed. Okay? So what we can do is, we can take delta G between 2 points of this reaction. And this delta G is going to tell us if the reaction starts here and ends here, by how much is the entropy of the universe going to change. Does it make sense? Raise your hand if it makes sense. It's fairly important. Yeah? Okay. So if we take delta G between 2 points on this graph, the delta G, by this relationship that I showed, tells us by how much is the entropy of the whole universe going to increase if the reaction proceeds from point A, well, from point Q to point P. Okay, so at this point, let's imagine that at point Q we have 80% reactants and 20% obviously products, and at point P we have 70% reactants. Just nod if that makes sense. Okay? So in this system where we have A plus B and C plus D, we move from a point where we have 80% A plus B and only 20% C plus D. We have the reaction happen all the way down to having, well, all the way down to having 70% B, 70% reactants, 70% A plus B, and 30% C plus D. Now I think I've lost you. No. Okay, raise your hand if I lost you. Okay, right. So the x-axis is the extent of reaction. We start with very, very pure A plus B, and we let the reaction happen. Okay, as it happens, some of A plus B is going to be converted to C plus D. And as we continue in the reaction, more and more A plus B is going to be converted into C plus D. Okay, and at the end, we'll have completely just C plus D. In theory, it may never actually happen that way, but let's imagine that this is what we call the extent of reaction. Maybe it's going to run just halfway through, we don't know. But let's imagine that we have different compositions of the system that we can imagine. Does it make better sense now? Okay? So at point Q, at point Q, let's say that we have 80% of A plus B and 20% of A plus B has been changed already to C plus D, okay? At point P, already 30% of A plus B has been changed to C plus D. And then it goes on and on and on and on and on, okay? Now, we can pick any 2 points in this whole reaction. We can look at their Gibbs energy values, take a difference, and we'll see what the difference is. Now, is the difference here going to be positive or negative? Huh? It's going to be negative, okay? Because we start at a high level of G and we go down, okay? So the difference between Q and P is going to be negative. What did we say does it mean? A negative delta G, what does it mean for the entropy of the universe? It's going to be going up. It's going to be positive, okay? So this process of going from Q to P, so turning some more A plus B to C plus D, is a process that increases the entropy of the universe, and therefore it's going to be a spontaneous process. It's going to happen. Okay, there were some questions there.
Yeah, but after the middle, will it be the reverse reaction?
We'll get there, yeah. But yes, you're correct. Okay? Any questions about what I just explained? Yep.
Why does it? What does it mean that it doesn't go to the bottom? It doesn't go to zero.
It's well. It never goes to zero, okay? It's actually the absolute value of G we can't really measure. We can only look at changes, okay? So this is kind of an arbitrary scale, okay? We don't really know where this is, okay? G to be zero, it probably would have to be at absolute zero, etc., etc. Okay, so it doesn't happen, okay? But the shape of the curve could be completely different. I just made it up. I just made up a nicely symmetrical curve, okay? But the curve could look like this, for example. Okay, I don't know, it depends on the specific reaction. Or it could look the opposite way, it could look like that. Or it could have a completely different shape, okay? So I just made it up this way, and it looks symmetrical, but it doesn't have to be. Actually, in most reactions, it's not symmetrical at all. Okay? Any questions now about the how this works? Now, okay, so as you correctly said, we can also have a point W and point X on the other side of the curve, okay? And we can say, well, what is the Gibbs energy going to be if we go from X to W? It's going to be positive. So what does it mean for the entropy of the universe? It would have to go down. So this process on its own is not going to happen. It's not going to be a spontaneous process. But on the other hand, in the opposite direction, that is going to be a spontaneous process because once again, the difference in Gibbs energy is going to be negative. Now, what happens here? That is the equilibrium. So basically, once the reaction gets there, it just stays there. Because that is the minimum value of Gibbs energy. And also, it's the maximum value of entropy of the universe, okay, for this specific. So if this is the curve of entropy, at equilibrium, it's the minimum of G and the maximum of S. So we go to the maximum point that our system allows for the increase of entropy of the universe. Going either here or here would decrease the entropy. That's not what we want. Well, that's not what we can do, actually. Does it make sense? Now, having said that, of course, you will see reactions that go in the opposite direction, okay? That go here or go here. For example, the synthesis of nucleic acids, okay? That's a type of reaction that goes in the opposite direction. So they do happen, but they're not spontaneous. You have to do some work in order to do that. And at the same time, the doing of the work and the processes that get you the energy to do the work have to increase the entropy of the universe by a larger value than the one that you decrease. Okay, so once again, I showed you what can and cannot happen spontaneously without any work that has to be done on the system. Those are the things that decrease Gibbs energy and increase the entropy of the universe. They just happen. okay? If I drop the chalk, okay, it's not the best example, but it will just happen. I don't actually have to do anything.
Aging.
Huh?
It's like aging.
It is, but that's probably an even more complicated example of what actually happens in aging. Okay, so that just happens spontaneously. We can have processes that do not happen spontaneously. For example, I can take the chalk from the ground and lift it. But that needs some work, and this work will increase the entropy of the universe by more than what I just did. Okay, bad example because we can't really see how entropy changes. It's still true, but it's much more difficult to see. Does it make sense? Okay, so this was very briefly what Gibbs energy is about. That Gibbs energy actually tells us something very fundamental about the whole universe. It's quite amazing because by just measuring the properties of your beaker, you can actually tell something about the rest of the universe. I think that's quite a fascinating thing. Okay. One last thing about this graph and this reaction and Gibbs energy. The other thing that you can see, by the way, obviously the change in Gibbs energy at equilibrium is 0, okay? And for those of you who had derivations and integrals, etc., if we look at dg, which is the tangent, it's going to be 0 there, okay? So really no change. At the specific instant, there is no change there. But the important thing that I want to mention here is that Gibbs energy, in addition to being this fascinating measure of the entropy of the universe, is at the same time a measure of the maximum amount of work that you can get from a system. So this delta G tells us something about the entropy of the universe, but it also tells us, because it's actually in joules, it's energy. So this delta G is also the maximum work we can get by allowing the reaction to go from Q to P. Okay? So it's the maximum usable work that we can get from a chemical system. This obviously is extremely important for biochemistry, for example, because we need ATP, we need our muscles to work, and we need to provide this work by some chemical reactions. Okay? And this is exactly what describes how much energy, in theory, we can use to do this work. And the last point I want to make is that, and it's obvious from the graph, this delta G depends on where you start and where you finish. It doesn't depend, well, it does depend, but it doesn't depend just on the type of reaction, what kind of reaction it is. It also depends on with how much reactants and with how much products you start, and with how much reactants and how much products you finish. Why is it important? I'm probably going to talk about it in a lecture about mitochondria, but I'll mention it now in case I forget. Who has heard of ATP? Okay. In textbooks everywhere you see that the hydrolysis of ATP releases energy, okay? The energy that can be used to do work and whatever, okay? Now, they will say a mole of ATP will release so much energy, okay? Well, that depends on how much ATP and ADP and water and phosphate you start with. So it's not something, and I'll repeat it when we talk about mitochondria, it may be a bit clearer, but the amount of work that we can get from a chemical reaction doesn't depend on what kind of reaction it is. There's nothing special about ATP that it has somehow more energy in it or something, okay? The thing that makes ATP a very good source of energy for work is that the reaction of ATP hydrolysis is kept far away from equilibrium. Very, very far away from equilibrium. So therefore, we can let it drop by quite a long time, quite a long way, and therefore we can produce a lot of work from it. But the ATP itself is not special in any way. Well, it is special, but not in this way, okay? So the only thing that determines how much work we can get from a chemical reaction is basically how far from equilibrium we are. The further away from equilibrium we are, the more work we can get from the reaction. The closer to equilibrium we are, the less work we can get from the reaction. Okay? That's the only thing that determines how much work we can get, how far from equilibrium we are. Otherwise, what kind of reaction it is, doesn't matter. Okay? We could use any reaction that, if our cells decided to use any reaction to use as this carrier of work, they could. They would just have to keep it very, very far away from the equilibrium. Yep?
So efficiency is based on how far you are from the equilibrium. But you said that before for a steam machine to be efficient, it needs to be equilibrated in somewhere.
Yeah.
So
this is not really about efficiency, okay? This is about how much useful work you can well, it's sort of is efficiency, but I would have to actually think about how it's related to the steam engine. Because for the steam engine, in a way, because it's about the ratio of the temperatures, in a way that also tells you how far from equilibrium you are. If that makes any sense. But there's the tricky bit that if one of the reservoirs is at absolute zero, the efficiency is infinite. Okay, which is a bit tricky because it doesn't really work here, really. Yeah, I mean, that's an interesting one. I would have to think about how this thing relates to the heat engine, okay? Because it sort of is efficiency as well. But does the basic concept make sense? Okay, all the things about are actually really fundamental, and even though you might not actually use them in your everyday work, I think they're very, very helpful in understanding how lots of interesting things in the universe actually work. How is it possible that they do that thing or that thing? Yeah?
And how is temperature related to that graph?
To this graph?
Yeah.
There's nothing about temperature on this graph. Okay.
I mean, how does it affect the distance from equilibrium? Like raising temperature does not reach equilibrium fast enough.
Yeah, that's the other thing, okay? Thermodynamics doesn't really talk about speeds of things. Okay? Thermodynamics tells us how far from equilibrium we are, and in theory, how much work or which way the process is going to go. How fast it's going to go has nothing to do with this. Okay? That's where chemical kinetics come in, and you're probably going to have something more about it in the next lecture about enzymes. Okay, so kinetics and thermodynamics are completely different things. We can find an excellent reaction that is very far from the equilibrium, but it will never happen because kinetically there is a problem. A famous example is a diamond. Okay, diamond is a thermodynamically unfavorable form of carbon. Okay, it is quite far from equilibrium. Diamond would like to turn into graphite, but it never does, or it does very, 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 very slowly. Okay, because kinetically, it's not a reaction that happens fast. Okay, so those two things, how fast things happen and whether things happen, are different things. Okay, there was a question. Yeah.
Is there any relation to the dissociation of an acid to this?
Sure. Any kind of reaction, well, any kind of process in the universe will do what I just explained. So for acid, if you have some acid plus water dissociates into H3O plus A minus, that's exactly the same thing as any other reaction. Okay? So the dissociation again is driven by dropping down Gibbs energy and increasing in entropy. It's exactly the same thing, and it will reach some equilibrium at some point. Okay? Yep.
Yeah, I didn't understand. Well, what makes ATP go up there? I mean, what's determining?
A very good question. If I said that ATP, that the capability of providing energy for work of ATP is dependent on how far from equilibrium is, the question is, well, how does the ATP get there? How is it kept so far away from equilibrium? And that's going to be what we're going to be talking about when we talk about respiratory chain. Okay, so it's the enzymes that use other kinds of energy in order to pump this ATP up this equilibrium, up away from the equilibrium. Okay, so there's other work that's done in order to get ATP there, and then we can allow it to drop down and use this work. Okay. Okay, thanks for your attention, and I'll see you later.